Welcome. Today we're diving into one-sided confidence intervals, a powerful, often overlooked tool because everyone loves the classic two-sided version. By the end of this video, you'll understand when and why one-sided intervals make perfect sense, and we walk through two real-world examples. First, a quick recap. A confidence interval gives us a range of probable values for an unknown population parameter, like mean or proportion, based on our sample data. The most common is the two-sided confidence interval. For a 95% two-sided interval, we split the 5% error or alpha into 2.5% in each tail. We're saying we're 95% confident that the true parameter lies somewhere between this lower bound and this upper bound. It protects us from being wrong on either side. But sometimes we only care about the error in one direction, just like in a one-tailed hypothesis test. Consider these scenarios. You're checking a new production process, and you only care if the efficiency is too low compared to the current process. Or you're testing a dangerous chemical. You only care if the concentration is too high. You don't care if it is too low. A one-sided 95% confidence interval provides either a lower bound only, in which case we say we're 95% confident that the true mean is at least this big. That is, we're concerned that the true value could be too low. Or an upper bound only, where we're 95% confident that the true mean is no more than this value. This is used when we fear the true value could be too high. Now let's see this in action. A company claims their light bulbs last at least 10,000 hours on average. A consumer group tests a random sample of n equals 36 bulbs and finds a sample mean X bar of 9,800 hours with a standard deviation of 600 hours. We want to construct a 95% upper one-sided confidence interval for the true mean. This is analogous to a left-tailed hypothesis test. In hypothesis testing language, we're asking, is there enough evidence that the true mean lifetime is less than 10,000 hours? We will use the Z distribution here. Some will use Z because the sample size is considered large enough. Otherwise, we can assume this 600 is the population standard deviation. The formula for the upper one-sided bound is X bar plus the Z critical value times the standard error. The standard error is the standard deviation divided by the square root of n, which gives 100 hours. Using the Z table or software, the Z critical value for a 95% one-sided interval is 1.645. On substituting, the upper bound is approximately 9,965 hours. So the 95% upper one-sided confidence interval is from -infinity to 9,965 hours. And then to interpret, we say we are 95% confident that the true mean lifetime is no more than 9,965 hours. Note that the company's claim of 10,000 hours is outside this interval. This result provides enough evidence against their claim. That is, we will reject the null hypothesis of at least 10,000 hours. Now let's look at the other direction, a lower bound example. A coffee roaster promises their gourmet bags contain no more than 400 calories on average. A consumer group tests a random sample of n equals 16 bags and finds a sample mean X bar of 398 calories with a sample standard deviation S of 7 calories. We want to construct a 95% lower one-sided confidence interval for the true mean. In hypothesis testing language, we're asking, is there sufficient evidence to conclude that the true mean caloric content is more than 400 calories? Since the population standard deviation is unknown and the sample size n equals 16 is small, we will use the t distribution. The formula for the lower one-sided bound is X bar minus the critical t value times the standard error. For one sample mean inference, the degrees of freedom for the t critical value is n-1, which equals 15. Using the t-tables or software, for 95% one-sided with df equals 15, the t critical value is 1.753. The standard error SE is 1.75 calories. The lower one-sided bound is thus approximately 395 calories. The 95% lower one-sided confidence interval is therefore from 395 to infinity. To interpret, we say we are 95% confident that the true mean calorie content is at least 395 calories. We see that the claimed maximum of 400 calories is inside this interval. This means we do not have enough evidence to reject the roaster's claim that the bags contain no more than 400 calories on average. That is, we fail to reject the null hypothesis. And that's how to use one-sided confidence intervals. Remember, they are perfect statistical tools to accompany one-directional hypothesis tests. Thanks for watching.